Okay, welcome back. So let's run this case in parallel. So we already have decomposed the mesh in parallel. We have the mesh in parallel for this run. So as you go into grid, you see that you have all the processors. So as you have 100 processors, you will have 100 folders there. So now to run the simulation, you open the settings and nothing changes. Everything is exactly the same. Okay, the only thing that you change is you want to use different discretization, but regarding to running in parallel, there is no new entry. The only thing that you need to do that now that you are running, see that here you have FLUBIO-Poisson. Now you need to say MPI run minus MP number of processors. Okay, so we have 4 processors, 4. We decompose the mesh. See here that you have 4 folders. Here you put 4, and then you can run in parallel. So you go here, put it, and you have the solution. So the idea, I think there's no need to say it, but the idea of running is parallel that you get faster convergence. Okay, you are using more processors, and also as you distribute in different nodes the memory, also you can run larger programs. But as you compare the parallel serial run, pretty much we should get the same results. So at this point we should have a solution. So remember that in post-prod fields you have the binary, so see that you have the times 0, 1, 2. As you enter here, see that now you have gradient and T. So you have four different folders because you have 4 processors. So for each time you will have that. So now we need to convert this solution into the Btk file. So to do that one, you have the FLUBIO fields that you run like this. And P means that you have it decomposed in 4. So if you run like this, you are going to put everything together into 4 cores, into one single file, Btk files, that you can visualize in part of it. So see that everything has been reconstructed into one single file. And you can do the same with the boundary fields. So see if FLUBIO boundary fields, okay, so 0 to 1, skip field, everything. So you can go like this, and you're going to have all the patches here. Okay, so now you can launch ParaView, and you can do the normal post-processing. Okay, so you go here, post-prod, Btk fields, and let me open this. And here you should have your solution. Okay, so starting and final. Okay, so initial conditions, and then you iterate. So this is a smooth case in a perfect mesh. So it converges in one iteration, and you have seen in the previous one that is you run with non-orthogonal mesh, etc., or the Kirschner mesh. You see that the convergence stays longer because you need to approximate gradients. Okay, so a big advice is that always try to have very good quality meshes because you accelerate the convergence, but that is not always the case. Okay, so if you have complicated geometries, it will be difficult. So that we're going to show you in different cases, okay, for more industrial meshes. But this is how you run in parallel. Okay, so again, you're going to have here in post-processing also monitors the residuals. So if you want to plot the residuals, you have the information. Nothing changed. Everything remains exactly the same. For certain boundary conditions, also you need to decompose this file. This is a single file that you give exactly in the same way as in running in serial. Everything is done exactly the same. Nothing changed. The only step is that when you convert the mesh, you need to have the mesh in OpenFOAM format and the number of cores that you would like to use, and then you convert it using gradient, and you should have the number of processors here. So that's all how to run FLUBIO in serial and parallel. Okay, very basic tutorial, and from this we are going we're going to work with more validation cases, but we're going to increase a little bit complexity level. So thank you for your attention. See you next time. Bye.